calculations with moles is going to be the topic in this second lesson in a chapter on stoichiometry. And this is going to be an important lesson. So students often begin to have a little bit of a disconnect with some of the calculations that we perform in this chapter. So we're going to make sure that you not only know how to perform these calculations, but that you understand why you're doing what you're doing. We're also going to introduce a few concepts like the molecular weight, the formula weight, and the molar mass. And we're going to explain the similarities as well as, more importantly, the differences between those three. We're also going to introduce the mole-to-mole ratio, which is going to be super important for a lot of the calculations we do with moles, both in this lesson as well as at the end of this chapter. Now, my name is Chad, and welcome to Chad's Prep, where my goal is to take the stress out of learning science. In addition to high school and college science prep, we also do a variety of test prep, including the DAT, the MCAT, and the OAT. Now, this lesson is part of my new general chemistry playlist, and I'm releasing a few lessons a week throughout the school year, so if you want to be notified every time I post a new one, subscribe to the channel and click the bell notification. All right, so we first got to talk about what in the world is a mole. And students often get all the way through this chapter and still don't understand that a mole is just a number. In the same sense that a dozen is a number. If I said, I have a dozen donuts, and then I said, how many donuts do I have? You'd say 12. And if I said, I have a baker's dozen of donuts, you might not know this one, but you might, and it means I have 13 donuts. And the idea is that when a baker makes, a dozen donuts for the customer, he actually is going to make 13 donuts. That way he can give 12 to the customer and save one for the baker. So a baker's dozen means 13. And if I said I have a gross of donuts, and this one's even less commonly known, but a gross means 144. It would mean 144 donuts. And so, but the idea is that whether I use the term dozen or baker's dozen or gross, these are all just names that mean a specific number. Well, a mole is just another one of those, but the number it means is huge. It is 6.022 times 10 to the 23rd, and that is Avogadro's number. Now, it's Avogadro's number, but Avogadro didn't put his own name on this, so don't be like, oh, Avogadro's so conceited. He put his name on a number. So it actually, long after he was dead, somebody else put his name on this, so don't poo-poo on Avogadro here. But this is his number. So if I had a mole of donuts, it would mean I have 6.022 times 10 to the 23rd. Now, one thing to note about this number, I'm probably going to drop that last two. I probably most commonly only express this to 2 decimal places rather than 3, but some people will have you include that third, so I put it up there to begin with. But just note it that throughout the rest of this chapter and even the course, I'll probably cap this at 2 decimal places and say 6.02 times 10 to the 23rd. Now, if I did have a mole of donuts, you should call me crazy because a mole of donuts doesn't exist. A dozen donuts, no problem. A baker's dozen, great. A gross of donuts, no problem. A mole of donuts, if you had a mole of donuts on the earth, it would be pretty much donuts filling up the earth. You'd look in outer space and you just see about a big giant ball of donuts covering the earth. It is a ridiculous number that doesn't exist. So the idea is that you're never going to actually use this number outside the realm of chemistry. It's such a large number that pretty much nothing you're ever going to deal with, there's ever this many of. But in the realm of chemistry, atoms and molecules are so tiny that you're going to deal with this number of atoms or molecules all the time. Like in a typical glass of water, you'd have way more than this number of water molecules. And so that's kind of the idea. But in everyday life, outside of the realm of chemistry and dealing with atoms and molecules, you're probably not going to see this number. So, we're not going to talk about a mole of donuts or a mole of basketballs or a mole of anything other than probably atoms or molecules, FYI. All right, so that's what a mole is. And, where exactly this question comes from, we'll get to a little bit later. But let's just say I had 1 mole of carbon atoms. And my question would then be, well, how many carbon atoms is that? And again, think of this as just saying I have 1 dozen carbon atoms. So how many carbon atoms do I have? Well, you should say 12. And in the same sense, if I say I have 1 mole of carbon atoms, you should now say, well, you have Avogadro's number of carbon atoms. You have 6.02 times 10 to the 23rd carbon atoms. And so a mole always means that number. That's the first part. Now, what if I had 2 moles of carbon atoms? Well, then I'd have double that number of carbon atoms. What if I had 3.5 moles? Well, then I'd have that number times 3.5 carbon atoms, so on and so forth. But there's always this relationship between moles and the number of atoms or molecules. Now, I could say between moles and the number of whatever you're talking about, but again, you're pretty much only going to be talking about atoms or molecules, not donuts or basketballs or anything you're going to deal with in everyday life. All right, so that's the connection between moles and the number of atoms or molecules, but it turns out there's also another connection related to the weight of something, and it turns out this is inherent. This is kind of what Avogadro is getting at. Avogadro is giving credit because he related that the number of particles was proportional to the mass of a sample. And so it turns out that somebody came along and said that if you look at a typical atom of carbon-12, if you divide that by 12, we're going to invent a new unit. So rather than trying to measure that out in grams, we're going to call that a new unit called the atomic mass unit. So 1/12 of a carbon-12 atom is 1 AMU. And notice they could have also tried to relate it to, one hydrogen 1 atom, the most common isotope hydrogen 1 of its atom, that would be 1 AMU as well. And it'd be almost exactly the same number. But that's this atomic mass unit, and so because of that, a couple things are going to happen here. So 6.02 times 10 to the 23rd atomic mass units. Another name for this is, by the way, Dalton. So Daltons and atomic mass units are exactly the same thing. If you're in general chemistry, you're probably going to exclusively use atomic mass units. If you're in, a biochemistry class, you're going to almost exclusively use the word Daltons, but they're the same thing, FYI. All right, so it turns out that Avogadro's number of atomic mass units is equal to 1 gram. So this is your connection now between grams and Avogadro's number. And this is going to be important, as we'll see here in a minute. So if I told you again that you have 1 mole of donuts, how many donuts do you have? And again, you have 6.02 times 10 to the 23rd donuts. But if I said, how much do those donuts weigh? Well, you'd have no idea. I mean, if you knew the average weight of all the donuts, you could take that average weight and multiply it by 6.02 times 10 to the 23rd, but you don't just inherently know. But if I say, what is the weight of, say, 1 mole of carbon atoms? Well, again, that's 6.02 times 10 to the 23rd atoms, but the question is not how many do you have, it's how much do they weigh? And only because somebody actually tabulated this all on the periodic table are you going to know. And so it turns out there's a couple different ways we can look at this. We can say that 1 carbon atom, and look on here, and it's 12, and I'm going to carry that 0.011, and actually I'm going to round that. Yeah, we're going to round that. Equals 12 atomic mass units. And it turns out, this number kind of gets a little bit crazy in terms of talking about one single atom because it's really an average. But we'll really see what this means in a second. But if I said that I have 1 mole of carbon, or 1 mole of carbon atoms, again, that's 6.02 times 10 to the 23rd carbon atoms, that would equal 12.011 grams. And so what's nice is we have this scale. I can talk about 1 atom and it weighs 12 AMUs, or I can talk about a whole mole of atoms and it weighs 12 grams. And so when you're talking about a single atom, you can call that the atomic weight. But if you're talking about an entire mole of atoms, then you would call it the molar mass. Now, what if you're not dealing with a single atom? But what if you're dealing with a compound? Well, if you're dealing with a compound, we've got a couple of different options. So down here, I've got some carbon dioxide molecules. And the big thing here is that carbon dioxide being made of all nonmetals, carbon and oxygen, both nonmetals, is a molecular compound. So it actually exists as molecules. And in every carbon dioxide molecule, there's 1 carbon and 2 oxygens. But they exist as these individual discrete molecules. But not all compounds are molecular compounds. If you recall in the last chapter, we named molecular compounds in one lesson, but in a different lesson, we named, say, ionic compounds. And so over here, we've got sodium chloride. And we see that it doesn't form like individual molecules, like with 1 sodium and 1 chlorine. That doesn't exist. And so because it's not a molecular compound, we're going to have a hard time using the term what we call molecular weight. And that's the next introduction here. So with molecular compounds, we introduce a new term called molecular weight. And you just add up the atoms in the formula that are in each individual molecule. And so if we look, we take carbon 12.011 and then 2 oxygens, 2 times 15.9994, and add that together, and you would get a molecular weight now of 44.01 AMUs. 44.01 AMUs. That's its molecular weight. Now, if I said, what's the molecular weight of sodium chloride? That would be an idiotic question. It doesn't have one. It's not a molecular compound, so it can't have a molecular weight. And so instead, they came up with this new term for ionic compounds like this, that for all compounds that are not molecular, and they came up with what's called the formula weight. And technically, you can apply this formula weight to any compound, and it's just the weight of one formula unit, we say, one of the formula. And so even though in sodium chloride, if you have a big cube of sodium chloride, there's going to be tons and tons of sodiums and chlorines, but when we deal with formula weight, you're just going to look at whatever the chemical formula is, in this case NaCl, and add up the weight of that. So in this case, 1 sodium, 1 chlorine, we'd get that sodium, it'd be 22.99, and then we get the chlorine here to be 35.45, and we add those together, and we'd get a formula weight, instead of a molecular weight, of like 58.44 AMUs. Okay, now that's for, again, one molecule or one formula unit is the way we'd express that. But we can also talk about an entire mole again as well for both of these. And if I'm talking about a mole of CO2 molecules, then we'd say a molar mass would be 44.01 grams or grams per mole. Same thing here, we could have said grams per mole. Cool, and so we'd use the term molar mass. And same thing over here for NaCl. If we want 1 mole of NaCl, that would be the molar mass. And so molar mass is not going to have a distinction between molecular compounds and ionic compounds. It's just going to be called molar mass. And in this case, that molar mass would once again be 58, that doesn't look like an 8, 0.44, but now grams per mole. Cool, so if you want to talk about one individual molecule or one individual formula unit, we have molecular weight and formula weight. But if you want to talk about an entire mole of either one, it's just molar mass either way. Cool, now this molar mass is really important because this molar mass, whether it be the molar mass of a single atom, like this guy here for carbon, or for an entire compound like for either CO2 or NaCl, that molar mass is always the connection between grams and moles. And that's going to be one of the first calculations we do, is this conversion from either moles to grams or grams to moles. And either way you're doing it, your connection is always the molar mass. And the question will just be, are you going to multiply by the molar mass or divide by the molar mass? And we'll use some dimensional analysis to figure that out. So let's make some room here. All right, so let's start with this 1 mole of carbon. Again, my first question is, how many carbon atoms do I have? And in this case, that's going to equal Avogadro's number, 6.02 times 10 to the 23rd carbon atoms. But my next question is going to be, how much does it weigh? And 1 mole of carbon, again, that's what's on the periodic table. They published 1 mole of every single element in grams on the periodic table, or in AMUs for each individual atom instead of moles. But in this case, that'd be 12.011 grams, and I'm just going to round that to 12, so this would also be the equivalent of 12 grams of carbon. And so if I said I've got 1 mole of carbon, I could say, how many carbon atoms do I have? Avogadro's number, 6.02 times 10 to the 23rd. I could say, how much does it weigh? 12 grams. But students often get confused at what I'm even asking. And I'll ask them, hey, how many carbon atoms do I have? And instead of giving me Avogadro's number, they'll say 12 grams. Well, I didn't ask you how much it weighed. I asked you how many atoms I have. Or I might say, I've got 1 mole of carbon. How much does it weigh? And they'll say Avogadro's number, not 12 grams. So you've got to understand what question's even being asked. It's kind of like saying, hey, Chad, how old are you? And I say 175 pounds. And that's not the question answered. And then you say, well, Chad, how much do you weigh? And I say 45 years old. And I'm not answering the right questions. It's exactly that kind of a thing. So again, if I have 1 mole of carbon, the question is, how much does it weigh? 12 grams. How many atoms are there? 6.02 times 10 to the 23rd. So that's kind of the way this works. So let's say we've got 3 moles of carbon, 3 moles of carbon. Now we're actually going to look at the dimensional analysis and say, okay, how do we actually calculate the number of atoms or the number of moles? Now, to the number of atoms, Avogadro's number is always your connection between moles and the number of atoms or the number of molecules. And so in this case, we're going to put carbon atoms. Actually, we need moles on bottom. So we need moles of carbon on bottom to cancel with our dimensional analysis, and carbon atoms on top. And your connection, again, is always 1 mole is the equivalent of Avogadro's number. So we'll put 1 mole down on the bottom, and then 6.02 times 10 to the 23rd on top. And that way our moles of carbon are going to cancel. And in this case, 3 times Avogadro's number is going to be 18.06 times 10 to the 23rd carbon atoms. That is definitely not proper scientific notation, so we'll move that back over 1 spot, but allow us to do the math in our head, and 1.806 times 10 to the 24th carbon atoms. And so we have this connection now between moles and the number of atoms or molecules, and that connection is always going to be through Avogadro's number. And again, if you're going from moles to atoms or molecules, we ended up multiplying by Avogadro's number. If we were going from atoms or molecules back to moles, we'd end up dividing by Avogadro's number, but just let the dimensional analysis work it out for you, whether or not you're multiplying or dividing. Now, going the other direction, the question might be not how many atoms we have, but how much do they weigh? And the connection between moles and grams is always through the molar mass. And so in this case, go in the opposite direction. We might take 3 moles of carbon and say, how much does it weigh? Well, we want to know the relationship between moles of carbon and grams of carbon to get there. That way this cancels yet again. And in this case, 1 mole is always whatever the value on the periodic table is. So in this case, 12 grams, or really, I guess I should write 12.011, but I'm going to round it. As long as it's close to a whole number, feel free to round it. If it's not close, like, if you've got magnesium over here, that's 24.3, that's not close to a whole number, don't round it. If you've got chlorine over here, that's like 35.45, that's not close to a whole number, don't round that one. But like carbon at 12.01, yeah, go ahead and round it. Oxygen's at 15.99994, that's like 16, feel free to round it. Now, if your instructor, professor, teacher says, carry it to 4 decimals, well, then you're on the hook. Just carry it to 4 decimals, do what they say. But if you're just doing calculations and want to make sure you're getting, pretty darn close to the right answer, that's kind of my recommendation, is just if it's close to a whole number, just round it to the whole number. If it's not close to a whole number like magnesium or chlorine though, don't round it to a whole number. Carry an extra decimal or 2. All right, and so 3 times 12 would equal 36 grams of carbon. And so we can kind of look at this now that we've got this map. And there's a connection between moles and atoms or molecules. And that connection is always through Avogadro's number. And again, whether or not you're multiplying or dividing will just depend on which direction you're going. Are you going from moles to atoms or atoms or molecules back to moles? And then there's also going to be a connection between moles and grams, or I guess I could just write mass. And that connection between moles and grams is always going to be through the molar mass. And that molar mass comes right off the periodic table. And you're always going to have one of these periodic tables handy. So they're going to be on the wall in all likelihood in your lecture halls or classrooms. They're going to be in the front cover or back cover of your textbooks. I've seen them in tattoos on people's bodies. I've seen them on t-shirts and socks and credit cards, and I've seen them everywhere. So you're going to have access to a periodic table in one way, shape, or form, or at least you'll be able to look up one. So most classes don't require students to memorize all these, except sometimes we like to torture high school students and make them memorize like the first 30, or sometimes we just like torturing them even more and make them go further. But normally, we don't require students to memorize all of the periodic table because we're going to provide you one in one way, shape, or form pretty much just about any time. But if you are on the hook for memorizing it, I apologize. But for the rest of you, don't memorize this thing. I don't have the whole thing memorized either. So, but you definitely want some familiarity with like a lot of the elements and what the symbols mean. You should definitely know that like Na is sodium and things of a sort, and definitely know at least the first 30, know what the symbols correspond to and stuff, so that when I say zinc, you're like, oh yeah, Zn is zinc, and things of that sort. All right, so now that we've kind of got the way this map works, there's always this connection between moles and atoms, molecules, and moles and grams. Now we're ready to do some calculations. Let's have a little fun here. All right, so now we're going to do some typical calculations. We're going to be answering 3 questions. We're going to have a 300-gram sample of calcium carbonate, and the questions we're going to answer is how many moles of calcium carbonate do we have? What's the number of oxygen atoms in the sample? And what is the number of grams, or what is the mass of carbon atoms in that sample? So that's what we're going to be dealing with. And one thing to note here, so I've just moved our little map up here. So all roads lead to Moleville is often what you'll hear people say, but you can convert grams to moles and moles to grams through the molar mass. You can convert moles to atoms or molecules and atoms or molecules to moles through Avogadro's number. But if you want to convert grams to atoms or molecules to grams, you're going to have to go through moles to get there. So that's kind of what's behind all roads go to Moleville. So as long as the calculation you're doing involves moles, you can get there directly. But if you're going from the mass to the atoms or molecules or vice versa, you're going to have to go through moles. So that's the idea behind that all roads lead to Moleville. So all right, so one thing we're going to do here is we're going to use really, really nice numbers. And the idea is that if we can use really nice numbers and you can understand what you're doing, well, then when you get a question that doesn't deal with nice numbers, hopefully you've got the process down. So I said at the beginning of this lesson that we're going to make sure that you not only know how to perform these calculations, but that you understand what you're doing. That does by no means mean that you don't need to learn the process of performing these calculations. So super important because, again, we're going to understand them with nice round big numbers and things of the sort. But, if you get like I have 1.5 times 10 to the 12th carbon atoms and, just big numbers or super tiny amounts of grams or, those are not nice numbers. They're not fun. But we're going to pick nice numbers that we can do in our head without even a need to pull the calculator out, at least to a significant extent, which is going to make this a little bit more understandable. So, all right, so let's answer that first question. So how many moles of calcium carbonate? And so we're provided with the grams. We're right here, and we're asked for the number of moles. And the connection between grams and moles is always the molar mass. And where do you get that molar mass? Right off the periodic table. And so in this case, we want to put grams of calcium carbonate in the denominator and moles of calcium carbonate in the numerator, and the molar mass is always the number of grams in 1 mole, and so then we got to get those grams, and again, we get that right off the periodic table. So we'll go over to calcium here, and it's right around 40 grams per mole, and then we'll go to carbon, which is 12 grams per mole, and then 3 oxygens, which are 16 grams per mole each. 16 times 3 is 48, plus the 12 is 60, plus the 40 is 100, and so calcium carbonate turns out has a molar mass of 100 grams per mole. And I picked that on purpose to make this a little bit easier. So, and here our grams are going to cancel. And 300 divided by 100 is 3. So nice math we can do in our head. So we've got 3 moles of calcium carbonate. Okay, so now we have a problem. So because the next 2 questions don't actually ask us about calcium carbonate, about CaCO3. They ask us just about the oxygen that's in there or something about the mass of the carbon that's in there. And that's a problem. And we have to introduce what's called a mole-to-mole ratio. And it's not as difficult as you think. So let's say that, in my family, there are 4 people. So me, my wife, and my boys. So that's 4 people. My question is, how many, assuming we're whole people, how many noses do we have? And you should say 4 because each person has 1 nose. And if I said, well, how many ears do we have? And then you'd say 8 because each person has 2 ears. And if I said, how many fingers do we have? Well, each of us has 10, so 4 people would have 40. And you're just using a ratio. You're taking advantage of the fact that that the ratio of noses to people is 1 to 1, of ears to people is 2 to 1, and of fingers to people is 10 to 1. Well, same thing here. In 1 calcium carbonate, there's 1 calcium. Just like in 1 of me, there's 1 nose. It's a 1 to 1 ratio. Same thing here. 1 calcium per 1 calcium carbonate formula unit, or 1 carbon per 1 calcium carbonate formula unit, but there are 3 O's, 3 oxygens per 1 calcium carbonate formula unit. That becomes a 3 to 1 ratio. And so these are what we call mole-to-mole ratios. We can relate them through the moles, which is where we most commonly do it. Now you can do it through the atoms and formula units, but you're probably most likely going to be doing it through the moles instead. So same thing, notice instead of talking about 4 people, let's say instead of talking about my family and there's 4 people, let's say we're talking about my church and there's 4 dozen people. And the question would be, well, how many dozen noses are represented in my church? Well, 4 dozen. And if I said, well, how many dozen ears are there? Well, again, 4 dozen people would have 8 dozen ears in this case. And so there's 2 dozen ears per 1 dozen people. It's a dozen to dozen ratio. Instead of doing it right at the person level, we can do it at the dozens of person level as well. Same thing here. Instead of looking at each individual formula unit, we're going to look at the entire mole of calcium carbonate and know that there's 1 mole of calcium. So per 1 mole of calcium carbonate, 1 mole of carbon per 1 mole of calcium carbonate, but there are 3 moles of oxygen per 1 mole of calcium carbonate. We could also relate the number of moles of calcium to carbon in the sample, 1 to 1. The number of moles of calcium to oxygen in the sample, 1 to 3. Relate the number of moles of carbon to oxygen in the sample, 1 to 3 as well. Lots of different mole to mole ratios all tied up in this little formula. You can take any individual element related to the whole thing, or any 2 elements related to each other, and just using these lovely subscripts to determine those mole to mole ratios. Okay. So far, if I wanted the number of oxygen atoms now, well, again, the number of atoms, I want to get to right here on my map. How do I get to atoms or molecules? I get there from moles. But we have to be talking about the same thing. So if I want to get to the number of oxygen atoms, I have to come from the number of moles of oxygen. Well, we don't know the number of moles of oxygen yet. We know the number of moles of calcium carbonate. But I'm going to start there. If I hadn't already performed this calculation to get the moles of calcium carbonate, that would be the first thing I'd do. We'd still repeat this part right here. But in this case, we're going to take that 3 moles of calcium carbonate, and now we want to determine the ratio of moles of oxygen to moles of calcium carbonate. And that mole to mole ratio, the first place this is coming from, again, is right from the formula of a compound is the first place we'll get them. We'll find out later on that we can also get them from the coefficients in a balanced chemical reaction to relate the different compounds, reactants, and products in a chemical reaction. But for now, in this lesson, we're just going to get it from the little subscripts within a formula here. And so in this case, there are 3 moles of O, 3 moles of oxygen atoms for every 1 mole of CaCO3. So there's 3 O's in 1 formula, so to speak. So it's a 3 mole to 1 mole ratio. And with our dimensional analysis, that's why we needed to put the moles of calcium carbonate in the denominator so they'd cancel. And 3 times 3 is 9. But this question, we don't want to stop there. So this question didn't want the number of moles of oxygen atoms, it just wants the number of oxygen atoms. So now we're here at 9 moles of oxygen atoms. We want to get to the actual number of atoms, not the number of moles of atoms. And that's always through Avogadro's number. And so in this case, we're going to put moles of oxygen on the bottom so it'll cancel. And then we'll put the number of oxygen atoms on top. And 1 mole always has Avogadro's number, 6.02 times 10 to the 23rd. So in this case, 3 times 3 is 9, and times Avogadro's number, looks like I need a little space here. And so notice 9 times 6 is 54, and 9 times 0.02 is 0.18. So 54.18 times 10 to the 23rd. And again, you could also just use your calculator, but again, this is not proper scientific notation, so we'll just move that over 1 decimal place and get 5.418 times 10 to the 24th, and that is now oxygen atoms. Cool. And I'm not worried about sig figs just yet, FYI. Don't care. I've got obviously 4 sig figs that is that appropriate or not? Don't care. Not the point of this lesson. All right, so the last question that I erased there, off to the end there, was the number of grams of carbon in the sample. And so I want to get to the number of grams of carbon. Well, to get the number of grams of carbon, I have to know the number of moles of carbon. And right now, we don't know the number of moles of carbon, but we do know the number of moles of calcium carbonate. And again, we can relate the moles of calcium carbonate to moles of carbon through a mole-to-mole ratio. So again, had we not already calculated that we have 3 moles of calcium carbonate, that would have been the first part of the calculation, but we have, so I'm going to start there. So the 3 moles calcium carbonate. And now we want to relate the moles of carbon to the moles of calcium carbonate. And once again, we'll get it right from the formula. There is 1 carbon, so 1 mole of carbon in 1 mole of calcium carbonate. It's a 1-to-1 ratio. And so in this case, in our 3 moles of calcium carbonate, we have 3 moles of carbon. But again, we want to convert that into grams now. And again, the connection between moles of carbon and grams of carbon is always that molar mass right off the periodic table, 12 grams per mole here. And so we'll put moles of carbon on the bottom, grams of carbon on top, and it's again 12 grams is equal to 1 mole. And so we got 3 times 12, and that's going to get us 36 grams of carbon. Cool. And this represents the examples of pretty much the standard kind of calculations you're going to see. And again, I use nice big numbers. You're going to want to definitely get some practice in. And I'd recommend, if you can, get nice big numbers first, but then work your way into some ugly numbers. Instead of 300 grams, what if this had been like, 1.736 times 10 to the negative 13 grams? Then we wouldn't have been doing this in our head. We would definitely pulled our calculator out from the beginning. So, but super important in my, opinion, that we start this out with numbers, that we can do a lot of the work in our head so we don't get lost on the math. Now, if you found this lesson helpful, a like and a share tells YouTube to share it with other students who might find it helpful as well. And if you've got any sort of questions involving calculations with moles, feel free to leave them in the comment section below. If you are looking for practice problems that have lovely written solutions and even video solutions, check out my General Chemistry Master course at chadsprep.com. I'll leave a specific link to the course in the description. A free trial is available. Happy studying.